Unity Water is proud to sponsor this podcast series because we believe great news, great solutions and great outcomes deserve to be shared. See what we're all about at unitywater.com. You're listening to the Australian Water Association's podcast series.
I'm Hazel Flynn, and with me now are Chris Pipe-Martin, Water Product Quality Program Leader at Logan City Council, and Reg Bailey, Work Package Design Manager at Logan Water Infrastructure Alliance. Welcome, gentlemen.
Hello, Hazel.
You're here to talk about a very interesting way that you met a challenge being presented to the drinking water in the Logan City area in Queensland's southwest. Chris, what was the problem?
Well, Hazel, Logan City is a growth area, and the state government in particular has got a priority development area in the southwest of Logan City where it's planned for an extra 120,000 people to move in over the next 10 to 20 years. So Logan City Council is required to supply water and wastewater services to that new community. We established the Round Mountain Reservoir as a way of servicing water to that community. But we realised that initially, because the population would be low, that it would take a long time for that water to turn over in the reservoir. Water age in our network would be long, and that means that we would lose disinfection in the water going to the consumers, which is not desirable. So we needed to find a way of maintaining the disinfection of that water going to the consumers. One of the big problems we had is that the reservoir is about 4 kilometres from the nearest established area and the nearest sealed road. So we could only bring in equipment along an unmade road or an unsealed road, which becomes impassable in wet weather. And wet weather in the middle of summer is the highest risk time for us in terms of water quality. So we wanted to be able to make sure that this chlorination facility that we wanted to put in would operate during that summer high risk period. And that was going to be a problem when we wouldn't be able to get deliveries of chemical to the site because of the impassable road. The other problem was that there was no mains power to the site. That was also about 4 kilometres away, and it was going to cost a lot of money to bring mains power to that site. So we were tasked with providing a treatment process which could operate 12 months of the year, and also powering that when there was no available power, and it was going to cost us maybe $1 million to get power to that site.
So some big challenges. How did you go about looking at options that might address those challenges?
Well, we looked at the conventional things first. In this sort of situation, it would be normal to put in a sodium hypochlorite dosing system, which is sodium hypochlorite is your pool chlorine. So we would have bulk deliveries of that sodium hypochlorite to site. There would be a storage tank on site, and then that sodium hypochlorite would be dosed into the water supply going to the consumers. With sodium hypochlorite though, it does degrade quite quickly, and it also produces some undesirable byproducts. So we minimise the amount of time that we store that chemical. We don't like storing it more than 2 weeks, so it doesn't have time to degrade and produce those undesirable byproducts. And as I was saying, our high risk time is during the summer wet period, so it would be quite conceivable that during that period we would run out of chemical and not be able to deliver any more chemical to the site. So we wanted to look at alternatives where we will be able to run the chlorination facility for extended periods of time during wet weather without having to take bulk chemical deliveries to the site.
So you've crossed off option one, then what happens? What do you consider next?
We looked at a couple of other options. One was electrochlorination. So this is a process where you take salt, dissolve it in water, and you put it through an electrolysis cell, something similar to your saltwater chlorinator in a swimming pool. An electric current breaks down that salt into sodium hypochlorite and hydrogen gas, and then that hypochlorite can be stored on site and dosed as required into the water supply. That gets around some of our problems with delivery because it means that we can take dry, bulk packaged salt to the site and have quite a big stockpile on site, which means we don't need chemical deliveries on a fortnightly basis. So that seemed an attractive option. We just needed to look at the practicality of running that sort of system because it's not one that we had run before. There were a couple of other options. Chlorine gas deliveries are also an option for water treatment. That was discounted fairly early just because of some of the hazards of using chlorine gas and the unfamiliarity of our operators with that process. And there are other processes as well, like calcium hypochlorite solution. So calcium hypochlorite is the granular pool chlorine that you use in your swimming pool. We could have had that delivered to site and also dosed into the water supply. But once again, we don't like storing large quantities of that chemical, and that was going to be a problem during the wet period.
So Reg, what was the next step then? Once certain solutions had been looked at, discarded, there was a plan to go ahead, what happened next?
Well, we were given the task then of designing a solar-powered electrochlorination system to be installed on the site. One of the first things we had to do is size the system. We had to calculate how much chlorine we needed to produce. This was based on a number of variables. We didn't have control over everything, but we made some assumptions, and at the end of the day, a decision was made on a 32 kilogram electrochlorination system. So that's 32 kilograms of chlorine produced every day. The next question is how much energy do we need to produce 32 kilograms of chlorine? Basically, we need 5 kilowatts of electrical power to convert salt into 1 kilogram of chlorine. This was the basis of then designing or sizing the solar-powered electrochlorination system. Apart from just converting the salt into chlorine, there's pumps, blowers, chillers, a lot of other equipment that had to get powered. So from that, we calculated we needed a 87 kilowatt solar array on the reservoir roof. To give you an idea, that's probably 20 times the size of a large domestic solar array. We had to install it on the roof because of our concerns. There's lots of evidence of vandalism on the site because of its remote location. So the next challenge was how do we install all these panels on the roof that was never designed. We needed walkways, handrails, we needed to do inspections and maintenance on the solar array. So there's quite a bit of design work just went into the solar array side of it.
So you had a few hurdles to solve that wouldn't necessarily have been apparent at the beginning. Was there anything else about it that was surprising?
Probably the biggest unknown issue that we came up against was dealing with the hydrogen gas. That's a byproduct of electrochlorination. The equipment that we'd decided to purchase is manufactured in the UK. We're buying it through a vendor based in Western Australia, and it has to comply with the regulations, the Queensland regulations. So there was some modifications required to the equipment. We had to make sure that we weren't voiding any warranties or doing that, but at the end of the day we couldn't switch it on before the Queensland accredited assessor had said it complies with the regulations.
So how long was the process from deciding that you were going to go with this solution to actually being able to throw that switch?
I think the actual delivery of the solution was fairly quick, Hazel. The decision process took us quite a long time. I mentioned before the various options we looked at. We then had to go and cost all those options and make sure that we were achieving not only a sustainable solution, but one that was cost effective. So we looked at those 3 chemical dosing systems I mentioned before, and we looked at the capital cost involved, how much the equipment was going to cost, but also how much it was going to cost us to run that equipment over a 10-year period. And the electrochlorination system came out as the lowest cost option over a 10-year period. So that whole decision process probably took us about 2 years. It then only took Reg and his team probably 10 to 12 months to deliver the system once we'd made that decision.
And in fact, it's not just a great solution for this particular problem, it's an Australian first, isn't it?
We understand, certainly from the research we've done, that no other water supply authority in Australia has adopted a solar-powered electrochlorination system.
Oh, well done and getting it happening. And it started operation in September 2017. How's it been since then?
The operation's been very good, Hazel. It's probably exceeded our expectations a little in terms of its reliability and the capacity of the solar plant to run the system under a variety of conditions. We originally thought that we would have reduced operation on cloudy days, but in actual fact the solar array has worked very efficiently to be able to produce chlorine consistently basically every day since we started. So that's been a great outcome. And also that dosing of chlorine into the water supply has greatly improved the water quality going to our consumers. So we can see the improvement in the water quality and the safety of the supply that we're providing to the consumers ever since we started up in September, October 2017.
So that's a real win-win.
It is, yeah. Look, we're really excited about this process because we think it's innovative, sustainable, and it has been cost effective. And it's also a model for other communities. You know, I could imagine small remote communities being able to use the same sort of technology, maybe on a smaller scale, but using this as a model for improving water supply in some of those remote communities where it's difficult to deliver chemical and a safe water supply.
Very promising and exciting stuff. Thanks for coming in and talking to us.
Yeah, thank you, Hazel.
Thanks, Hazel.
So that was Chris Pipe-Martin, Water Product Quality Program Leader at Logan City Council, and Reg Bailey, Work Package Design Manager, Logan Water Infrastructure Alliance, talking to us about a very interesting combination of micro power grid and electrochlorinator system, which is very promising for water utilities everywhere. And thanks for joining us.